Okay. Can you hear me? Yeah. Okay, I want to walk you into a minor disaster here. About 5 years ago, Amazon tasked one of its machine learning teams to look into building a machine learning tool for its HR team to help them hire faster and more efficiently. The company was about to embark on a massive hiring spree. Over the next 3 years, it would triple its global workforce. And recruiters were kind of dying under the weight of the number of applications and roles that they needed to hire for. And machine learning offered to give them a solution that would triage applications much faster, could turn a mountain of applications into a neat small pile of recommendations of top talent. Now, how could they do that? The company had been collecting hundreds and thousands of resumes over the past number of years for all the roles that they were hiring for, and they knew which ones went on to become successfully hired and went on to stay as successful employees. And so what they could do is they could train a model on all of this historical record of data, right? They knew which ones were successful and which ones were not successful in applying for jobs, and the machine would learn the rules to predict success and non-success in that setting. Now, about a year into that effort, the team discovered that it was up against a massive challenge. The algorithm, the model, was very biased against females for technical roles like software developer, okay? Not surprising if you know much about the tech sector. Now, how could that be the case? Well, the historical record of the company, much like all other tech companies in the Valley, is that they were hiring overwhelmingly males for those technical roles. So the machine learned learned the bias that was evident in that historical record and reproduced it. It was rewarded for doing so, right? All of the attributes of success contained maleness in it, and so it learned that bias. Now, to its credit, Amazon tried to get rid of that bias, but it found out it was actually a really, really hard thing to do. You could remove explicit mentions of gender or sex from people's resumes, but that left a lot of other things on the resumes that suggested a gender. Name is a good example. Activities explicitly or implicitly mention one's gender often. And if you could remove all of that stuff, you were still left with the language that people used, okay? The verbs and so on. It turns out that males who were hired, tended to use much more aggressive language, like they captured things, they executed on things. Okay, so it turned out to be almost impossible to remove bias from the reams of data that they wanted to use to learn on to predict who would be a good candidate and who wouldn't. So Amazon ended up shutting down that project. Now, not every machine learning project fails, obviously. There are some really good examples of ones that are successful out there, but a lot of them do stall at that phase of proof of concept, POC, or they're deployed out into the wild and very quickly reined back into the lab because they fail for reasons that the teams hadn't predicted. So I'd say, what we have here, at least in the enterprise setting, is a POC problem, right? It's a POC problem, proof of concept problem. A lot of projects end up stalling at the proof of concept stage. And I think there's a lot of different reasons for that. I'm not going to talk about all of them for sure, but I want to focus in on one that I think is particularly crucial and that gets not nearly enough airtime, particularly in this community, this design research community. And it's the problems that arise when we first deploy a machine learning tool out into the wild and it gets in people's hands. Okay, here's my argument in brief. We're focusing far too much on the end user at the cost of missing the huge challenge, the huge design challenge and research challenge that's evident in needing to understand the ecosystem of people, the village of people that are required to maintain machine learning tools once they get out there in the wild. We're stuck in the classical software paradigm where we think that maintenance is something that engineering teams do on their own in the background from time to time. Here's the thing, machine learning changes the game, okay? The table's been flipped, the paradigm is changing. Maintenance requires a massive effort on the part of a whole wide spectrum of users, not just technical users, not just machine learning engineers or data scientists, also the end user, also business admins who need to set rules around thresholding. When is automation okay? How much risk are we comfortable with taking? What kinds of risks? Should I be able to intervene regularly to decide when and what kind of human and when, what type of human under what conditions they should intervene in the process, and so on and so forth. People, teams collecting data to educate the machine so it can learn better in the future. People patching errors that are coming out of the model's output, and so on. So there's this wide range of, there's an ecosystem of actors, okay? And right now, we're not doing anything to design for that community, that ecosystem. We're not doing nearly enough to understand the needs and requirements of that community when we're building machine learning tools. And we do that at our peril. When we're releasing tools out into the wild and we don't have this ecosystem well supported by tooling and processes, tools end up failing. They end up misbehaving. They do all sorts of things that we don't want them to do. Hence why we have this POC problem. When people try to push it out, they see it fail, they don't know how to support it, they pull it back in. Okay, so let's take a step back for a second and ask, how is machine learning produced? So super high level, not going to get down into the weeds, and I'm going to focus here just on the supervised learning paradigm. That's the most common one that people are using or trying to put out there into production. So we're starting with raw data, right? This is the fuel that the fire burns on. You can't build machine learning without it. You're going to clean and pre-process your data, basically banging it into shape so that you can learn from it, learn effectively the kinds of rules that you want to perform the function that you want that model to perform. Depending on the kind of challenge that you have, you're going to select a candidate algorithm or a couple of them. You're going to train it on the historical data. You're going to optimize the parameters. You're going to go back and forth, tweaking the knobs of your algorithm, your model, until you find something that where the model is learning well from the data that you're providing to it. And eventually, when you feel confident enough, you're going to expose it to data it's never seen before to validate it or test it. Okay, and this is like exam season. You want to make sure that the model's learned the lessons effectively before you put it out there into the real world to go look for a job. You don't want it to have just simply learned the things that you taught it during the semester. You want to test to see whether it's learned the actual fundamental things behind those examples. So this is a heavily iterative process. You're moving back and forth across all these steps. Okay, so far so good, right? This can be a monumental challenge for some really big modeling efforts, but what we have at the end of this is a model, right? It's a model. It's not yet providing any value to anyone. Not until it's situated and embedded inside a feature or a product to solve a real problem for a real user is it going to do anything. And that doesn't necessarily mean that there needs to be a GUI attached to it. You don't need an interface per se that someone's going to be interacting with. It could just be an API endpoint or something, but it does need to be wrapped in a software that's going to be able to deliver value. And so that's this, right? The model building process is part of a much larger product building process or feature building process. Now, this is stuff that we know really well. Like, this is the bread and butter of design research. This is where we're doing our discovery research, our formative research to help the product teams formulate hypotheses about how to solve the problem that we've just framed. We're doing early evaluative research. We're working back and forth with product teams that do and don't contain machine learning efforts. This is something that we know really well. And eventually we get to a point where we're ready to ship. We feel like we've gained enough confidence in the hypothesis through our research and through our iterative testing that we're ready to ship. So there's this phase deploy where we're not really involved, hyper important, but it's not really a design activity per se. And then there's this long path that extends out before us where we're maintaining a product and improving on it. So these two steps here, build and improve, this, like I said, this is the bread and butter of design research and product design. This is where we're leveraging over time the design methodology and the research methodology to figure out what problems are worth solving for users and how do we approach solving them. By contrast, the deploy and maintain steps are things that we classically just think these are pure engineering activities, right? In a classical software context, these are things that we don't think too much about. Maybe in our research, we're collecting some technical requirements and working with tech teams on that stuff, but for the most part, these are things that we don't really think about. Insofar as we're working on a product team over time, we're helping the product team to iterate, to improve the product. We're not thinking about the paradigm of just maintaining, keeping the wheels on, right? Maintaining the product. But so here's the thing, right? Machine learning changes that paradigm entirely. Maintaining a product when it's a machine learning product is a massive effort, and it's an effort that can't be done by any single user group. It's certainly not going to be done by only a machine learning engineering team or only a data science team. It's going to require a whole host of different actors working collaboratively, and they're going to require product attention to do that well. Okay, that includes the machine learning engineer, the data scientist, the business admin who's might need to specify rules and criteria and thresholding and so on that allows for automation to happen at different times in the product life cycle and under different social and economic conditions, to people collecting data, to people patching errors, and so on and so forth. So what happens when things get out there in the wild? Like, let's talk about some of the specific things that make maintenance in a machine learning paradigm actually difficult and different from in the software example, the classical software example. I want to talk about this in the context of a use case. Sorry for the resolution here. This happens on these huge screens. A specific use case, just to make this real in people's minds. So optical quality verification, basically using computer vision in a manufacturing context. Computer vision is a type of machine learning where you'll take an image and turn it into some form of structured intelligence, potentially a classification. The easiest thing to think of is passing a photo of an animal and the machine deciding whether it's a cat or a dog, right? Everyone's seen these kinds of examples before. But computer vision can do an awful lot more complex things than just that. So using computer vision in a manufacturing context, specifically for producing these large spools of steel, to spot defects. Okay, this is a massive problem for manufacturers. They spend an awful lot of money either trying to manually or through some rule system spot defects and prevent them from going out the door, or they pay a lot of money in the consequences of not having spotted them in the first place. So how would we do this? We'd feed the machine an awful lot of historical images about, basically that show the surface of steel, some of which contain defects and some of which don't, and we're trying to teach the machine to spot the ones that have defects, or basically to separate the two classes, one on the one side telling us which have defects and the other telling us which don't have defects, and that would then in production be able to spot for us and alert us when there's a defect coming down the production line. So we deploy it, and then we'd show it images like this, okay? New images, and we'd ask on each occasion for the machine to predict for us, is this a defectuous or non-defectuous piece? And if it's defectuous, what kind of a defect? So you'd see output like this, right? No defect, it's a defect, and it's got scratches, and so on. So that's the basic mechanics of the tool. Okay, so the first big thing that people confront is the question around uncertainty and what to do with it. So very, very accurate models are often also uncertain about their predictions. Okay, this may seem counterintuitive, but it's normal and it's natural, and it happens in all models, and it'll depend on the kind of input that they're receiving. Not every input will be something that a highly accurate machine will be sure about. It may be confused, may be uncertain about whether it should fall into class A or class B. So let's look at these examples, the same ones I showed you just a second ago. Right, the classifications are there, no defect, scratches, and so on, and then the confidence levels are there. Okay, this is just for demonstrative purposes. I'm making this up, but it's to make a point that there are certain examples that the model is a lot more certain about than others. So 58% confidence is not a great confidence level for a prediction, right? Compared to something like a 99% or a 93%. So it suggests that the model is actually having trouble with that prediction. But it's still just making one prediction, at least in the way I've set it up. It's just telling it it's a defect. So if I didn't look at the uncertainty level, I wouldn't really know that the model wasn't sure about that prediction. So what's the intuition here? Okay, so imagine I'm asking the model to separate to train on the data and to be able to separate between defectuous and non-defectuous pieces, and it's learned the rules and is reducing it to plotting on this two-dimensional surface, this grid, so that we can see what's happening with the data, and you can see how the classes are being separated. Okay, so the red might represent, for example, defectuous, and the blue might represent non-defectuous pieces. And there's some class overlap, right? You see that there's not a clean separation. It's a pretty good model in the sense that the classes are being separated, but definitely not a superb model because you see this overlap of classes happening. So the model's going to learn a decision boundary. Okay, and what that basically means is that going forward, the model would guess that if a point lands on the bottom side of the line, it's going to guess that it's blue or non-defectuous, and above, it's going to guess that it's red or defectuous. But you can see that it's not always going to be certain because the data that it's learned on also is not cleanly divided on one or other side of the boundary. So imagine we've got a data point that comes in here. I'm clearly not a graphical designer, but imagine we've got a data point that comes in here and it's falling over here on this side of the spectrum, okay? So it's surrounded by blue points, it's far from the decision boundary, chances are high, well, for sure it's going to guess that it's a blue or non-defectuous piece, but chances are high also that it's going to have a high level of confidence about that. So you can think of a situation like this, right? It's pretty clear to the model that this is a non-defectuous piece and it's going to, it's going to guess with high confidence. Now imagine a situation like this where you get a piece coming in and for whatever reason, it's much closer to the decision boundary, and it's also in a place where you see that there's a certain amount of overlap in the classes. There are blue points up there mixed in with the red points, so almost certainly there's going to be a higher level of uncertainty here. Okay, for example, a piece like this where, okay, so there's surface stuff going on there. The machine is thinking that it's similar to other situations where it's not a scratch, but it's some other kind of defect on the surface. And it's going to guess that it's a defect, but it's really not that sure, 63% confident. Okay, so this is what we'd call data uncertainty, a type of uncertainty that's data uncertainty where we have a lot of information in this region of the graph, but we're not totally sure because there's actually the presence of both classes there, even if it's on the defectuous side of the decision boundary. Okay, contrast that with this example, far away from the decision boundary, on the defectuous side as well, but also in a place where there's no other data points, okay? So here's an example. So imagine, and again, I'm just imagining this, but imagine it sees something like this coming down the production line, and it's like, okay, wow. There's like a lot of lines going on there, and I've never seen an image with that many lines on it before, and I've never seen this kind of a pattern before. Remember what it was trained on, right? The images were just flat steel with different kinds of sort of amorphous defects on them. This, by contrast, a human would recognize this as a design pattern, but the machine knows nothing about design patterns. It wasn't trained to think in those terms. So it's like, okay, so there are edges on there. It looks something like a scratch maybe, because that's the only time I see lines on there, but also I've never seen lines that are so structured in this way. So you'll see that it's on the defectuous side of the decision boundary, but it's also pushed away from the rest of the data points. And that's a reflection of the fact that it's got characteristics that are different from other data points in the data set, okay? Okay, so why the heck am I talking about all that technical stuff at a design research session, okay? It's because identifying and dealing with these circumstances is in fact a really complex design decision, and if we're not thinking about it when we're building our products, we're missing a huge part of the challenge. We're missing a very important part of the structure that's going to be necessary to support a machine learning tool when it goes out there in the wild. So you can think of a range of different kinds of users that might that are in that ecosystem, okay? Like a plant, someone who's on the assembly line, someone who maybe is like a shift supervisor or something like that, someone with a bit more business responsibility, data scientist or machine learning engineer, and then someone down there who's on the assembly line, but who's there with a computer and who's probably doing some form of labeling or some sort of more expert review of things that are passing down the production line. Okay, so all of these are user types, right? This is normal for us, right? You can think of these as user types. And they're all going to play a role in different parts of this challenge. For example, imagine this point over here, right? We're really sure about it. Maybe we should automate that process, right? If something comes down the line and we're 99% sure that it's a non-defectuous piece, just let the thing roll, right? No one should review that. But the machine can't make that call on its own, right? The machine is good at predicting what something is, but the machine doesn't make the business rule that if the confidence is 97% or above, then I should let it roll down the line. That's a business decision, and it has to do with how much risk and what kind of risk the business is comfortable with, and at what point, and so on and so forth. So you're going to have someone who is like a business owner or an administrator or a shift supervisor or something who needs to have an experience in tooling that allows them to specify the criteria under which automation and non-automation happen, and at what point, and they need to be able to toggle this fairly well, and they need to be able to understand the trade-offs of doing so. Okay, so that's an intense design challenge, but it's a very different thing from designing the tool that the line worker sees when there's a new piece coming down and the machine is saying non-defect, defect. Right? If that's all we're designing and we're not designing something for the shift supervisor or business admin to toggle around automation, around confidence levels, then everything will either be reviewed by the human or will be automatically sent through regardless of what the machine's confidence level is, and that's a problem. Take this example over here, okay, low confidence. Almost certainly the technical team is going to want to review why the heck are we having these predictions come through that are low confidence, right? Can you please explain to me why it's low confidence? Okay, so there's an experience that can be built out around that, like a sort of data exploration or explainability challenge to help the technical team understand why we're seeing low confidence predictions. And they're quickly going to realize that this is in an area where there's like a very sparse amount of data on the manifold. And so one trigger response to that is that you need to go out and collect a lot more data in that area to remove the blind spot from the model. Okay, so the engineers are not going to be out collecting data on the floor. You're going to have to organize a data collection process, and that process is going to have to contain some tooling and some business process that allows people to go out onto the assembly line floor, capture images, label them, and then feed that intelligence back into the pile of data that we use to retrain the model the next time around. Okay, so a lot of that sounds pretty technical, but the overall point here is that there's an ecosystem of people who need to be present, need to be supported from a product perspective in order to make the machine learning tool run, in order to keep the wheels on, in order to improve the intelligence of the model over time. It's not just about building and shipping and worrying about whether the lights stay on or something like that, as we might, that's kind of an extreme form, but like as we might in the classical software approach. Machine teaching. So this is another paradigm similar. Basically, this is, again, about capturing intelligence that humans have that the machine might not yet have. Imagine an example like this, where the machine says, okay, this is not a defect, and I'm pretty confident. And it turns out that actually the machine's wrong, okay? So it happens that the machine is highly confident about things that it's wrong about. So just like humans, right? Humans often can be really confident about things that we're actually wrong about. Machines do this too. And so you need a process not just that's spotting problems when there's low confidence in the model's predictions, but also you need some kind of a sampling strategy to make sure that you're not allowing defectuous pieces that the model feels really confident about to get through. What does that look like? Well, it's going to depend on the risk level, the resource comfort of the team. The business user or shift supervisor is going to have to play a role, again, in determining what kind of a strategy, in conjunction, in collaboration with the technical users who understand the trade-offs on the statistical side a bit more. What kind of a process do we need to capture the intelligence of the humans when they look at this and know that it's a defect, but the machine is not making that call, so that the next time around the model is going to be trained with a corrected label and will hopefully not make that exact or similar error again in the future. 3, I'm speeding up a bit here because I know I'm over time, but data drift. So this is basically about the world changing. When we train a model, we're training a model on a snapshot of the past. Okay, you saw the data that I used to train the model was a whole lot of image data that I had taken not me, but that some people had taken at some point in the past. It was meant to represent all the different kinds of defectuous and non-defectuous steel pieces that I could imagine coming down that assembly line. I had to make some assumptions there, right? Like how big is the world of possible things that could come down the assembly line? It turns out the world changes after you do this, right? Here's some examples, right? Imagine my machine sees something like this. It's a steel surface with water droplets on it. Or here's another one, a steel surface with grease stains on it. Okay, imagine that there are processes inside the factory that change, and like the cleaning team is doing something, and every Friday now there's water vapor that is in the factory and collects on steel pieces that are lying on the factory. And so there's a structural change to the environment that means that new data like this is going to be coming into the machine on a fairly regular basis. My machine has never seen something like this before. My tool has never seen something like this before, so chances are high it's going to make bad decisions. Okay, so when data drift happens, you need a process, again, that involves this ecosystem of actors such that they can identify as early as possible when the environment is changing. Okay, and you can do that on the technical side, but you also definitely can do it by leveraging the people who are out on the factory floor so that they're collaborating about anticipating or observing when they happen changes to the environment, and then figuring out how to respond to them. You know, if this is something that you can't push back on, if water is going to be on your pieces from here on going, forward, you've got to find a way to retrain your model so that it captures that and that it knows that this is in fact not a defect. If indeed that's true. I've never worked on an assembly line, but if that's not a defect and that's not a problem, then you have to find a way of teaching your model that kind of thing. Otherwise, your model is just going to deteriorate in performance over time. Okay, so I hope the point has been clear that there are really important aspects of the maintenance of a machine learning system that make it very different from the classical software paradigm. And moreover, we need to be designing tooling and processes and experiences that support this and that allow facilitate collaboration across these actors. And moreover, it should change the way we approach the build and improve parts of our job, the things that we think are the bread and butter of how we do design research. We have to change the paradigm. We have to stop thinking that what we're doing is we're solving a problem for the end user. Of course we're doing this, but without the support structure, the user is the quality of the solution for that end user is going to deteriorate very rapidly, and the solution is going to be pulled out of production, and it will be a fail. Thank you.